Hello everyone, welcome back to the workshop, and we are here with the final talk for the day. And for this talk we have with us Professor Marcin Pilipczuk from University of Warsaw, and he'll be talking about solving hard-cut problems via flow augmentation. And as you might have been updated by the email, this is a fresh result. So this is completely new content for all of us. So thank you so much for joining us, Professor. Over to you now.
Thank you very much. Do you hear me well? Think.
Yes.
Yeah, thanks a lot. Okay, so this is based on joint work of Andrew Kim, Stefan Kirch, and Marcus Wallström, and some slides. I mean, there will be a few skeleton slides here that are made by Andrew Kim for her talk a few while back. But I will be doing many proofs with a pen on the tablet, drawing stuff. So I mean, not that many things will be on the slides up there. Okay, so I'm going to present you a new technique for solving CAD problems, which is called flow augmentation. And during this talk, I'll be focusing mostly on the technique and the proof of the technique. I won't be given much of the broader picture why it's important, but we'll discuss, why it's important in a moment. Okay, so I'll be presenting you a new technique that solves some CAD problems. It will be unfortunately only for undirected graphs. Directed case will be in the open problems part at the very end. And the interesting thing of this, one of the interesting property of this technique is that it's friendly to many weighted problems. Actually, it was designed with some weighted problems in mind, so that because if you know important separators, if you look at the important separators, one of the drawbacks of important separators technique is that it doesn't really work well if there are some arbitrary real weights on edges or vertices in the graph. And in this technique, it's devoted to problems where you have got some fixed cardinality bound on the cut size, and this cardinality will be the parameter, but also there are some other constraints like weights, but maybe some other constraints on the edges you need to choose, so that you're looking at not necessarily extremal cuts, so that the important separators technique won't work out. Okay. Just a word about the background. So the point is that one of our motivation to develop it was something that's called a coupled mean cut, which I won't define here, which was one of the undirected cut problems. It's actually quite weird if you look at the definition, but quite one of the undirected cut problems for which we didn't know before if it's W1 hard or if it's W1 hard or FPT, and now we know it's FPT. And it turned out that this new technique we developed was the last technique needed to settle some sort of dichotomy or sort of cut problems. I mean, that's like sort of very, very widely, but some in the properly defined in the CCP framework undirected cut problems. And that was the last missing technique. It turned out that all the missing cases turned out to be mostly without FPT, but I mean, the W1 hardness result were already known. There was a missing technique, the missing I of tractability. But that's for undirected. We don't know a lot about directed problems. For directed problems, there's big open area. I will discuss it at the very end. And what I want to say here is that, is that today I'm going to work with the flow. I'm going to show you the flow augmentation. I'm going to focus on the details of the applications of the technique and how it works to understand the bigger picture, like this, why do we do it? What's the CSP thing? And I mean, what's the bigger picture? What's the bigger picture of the applications and why we developed it? And why do we say that this is the missing technique for undirected graph cut problems? This won't be today, but I invite you now to parameterize complexity seminar when I'm invited. I think the final date is 19th of January, unless I messed up something. And then I will say again a bit of flow augmentation, but more briefly than today. But I will be speaking more about the background and like the CSP word up there and why we call it the missing technique now. Okay, so I'm going really to focus on the technique and a basic application for it, and the background and the CSP and like how it fits into bigger picture. That's for the seminar in January. Okay, good. So we are going for cut problems, and we think of problems like where we are looking for some cut or a union of some cuts to separate some things in a graphs. And in this talk, all our graphs will be undirected. So we are not thinking about directed graphs, they're undirected. So the very typical problem is to minimize the cut. You have got a graph, you have got some sink and source, and you want to cut the graph using minimum cardinality or minimum weight. You can cut edges or vertices. In this talk, we'll be mostly cutting edges. So that's one one of the typical problem. There was the multi-well cut problem that I guess you probably have seen today on the important separators lectures by Daniel Marks. I mean, there's like graph when you have got many terminals you want to separate from each other, and you want to cut the graph so that every terminal is its own connected component. Okay, so this is multi-way cut problem. There is multi-cut when there are pairs of terminals to separate from each other. There is, and we also think of directed feedback vertex set as a cut problem because it's really solved using cut techniques, and it's really about separating some stuff from each other. It's about cutting cycles, but it turns out it's very close to many cut problems. And today I heard you have seen the directed feedback vertex set algorithm presented by Daniel Marks. Okay, so those are the type of cut problems we're going to solve. And this is quite a vivid area in parameterized complexity. I mean, you have seen something today, but actually we have studied it for the last decade and more and developed a lot of techniques. And turns out that actually the algorithmic toolbox here is quite rich in the sense that you can solve a lot of problems. A lot of problems are tractable, but you need to do many smart and complicated things to get an FPT algorithm there. Okay. So let's go and very quick overview of the method so that you have got some sort of big picture of undirected cut problems. These are for undirected graphs. So you have seen gritty important separators. You have seen important separators, which think of like cutting out as much as possible from the graph using your constrained budget. And using these techniques, you can solve not only multi-way cut, but also the directed version. You can solve multi-cut using this sort of tricks. So it's quite versatile, but not completely. There is something called tree reduction, where you actually, if you have got a fixed sink and fixed source, then all the cuts of size most k between these two fixed vertices are actually constrained into a bounded tree graph. So you can use a lot of bounded tree routines. This is related to something called recursive understanding and randomized contractions, which is yet another technique that I think will be later in this course, will be discussed later in this course, where you actually can decompose the graph along small separators so that each bug of the decomposition is actually quite unbreakable. It cannot be really cut with small separators. For some definition, cannot be cut. I don't want to go into this and leave the floor, leave this one for people that will lecture to you later in this course. And there are some other things which are called this is called LP guided branching sometimes. So you look at some LPs, I mean, you look at some half integral relaxations, linear programming relaxations, or some CSP relaxations, submodular relaxations of some problems, and observe that actually they have got a lot of very nice properties, and you can use them to navigate branching algorithms. These algorithms are usually very efficient here, and but the applications is somewhat limited. I mean, there's a family of problems you can solve with this type of things, and for some problems it seems completely not amenable to these types. So these are the techniques we have here, and to our surprise, despite this big algorithmic toolbox, if we look at like somewhere properly defined family of all undirected cut problems with all different strange constraints on the cuts, we actually weren't able to solve some of them. And that includes coupled min cut that I won't define now. And it turns out that there's one technique missing, and this technique I will present you today. And I will use the following toy problem to solve, I mean, to motivate my technique. This is not exactly what was framework of the CSP that I haven't spoken about, but this is a very instructive problem. So I'm going to make a minimum cut problem, but it won't be a minimum cut, but I will have two different objective things. So I will have got a bound on the cardinality of my cut. So I want the cut between two vertices, edge cut, and or vertex cut actually on this picture, but it doesn't really matter. I want an edge cut or a vertex cut depending on the problem. But this is the cardinality of the cut, and this is the bound on the total weight of the cut. So I want to both optimize the cardinality and the weight. But I think of the cardinality as my parameter, and the weight can be some strange numbers I need to add, and I need to be, I mean, I can really only add and compare and cannot do any tricks with the number, with the weights here. Weights are complicated numbers written in binary. Okay, so this is my problem that I want to solve here. And the question is, where is FPT in K? And if you start thinking about making FPT in K in the undirected graphs, you can use the framework of randomized contractions. And so I haven't spoken about this framework. It will be later this course, so that may be a good exercise for you to actually solve this problem using randomized contractions. But you can do it, but it's actually quite complex. I mean, there's quite a complicated solution. You can employ this entire framework and work with. And actually, FPT in directed graphs is actually open. So I don't know it's FPT parameterized by K. I think this is like one of the key problems we don't understand about CAD problems in directed graphs. Okay, but we will start here in that. So we want to solve this problem in undirected graphs not using unrandomized contractions. So we want to make a simpler algorithm or a different algorithm or a more insightful or tailored to this problem algorithm. And our starting observation is the following, that if K is the size of minimum cut, so this, okay, so let's say that these are edges here. Sorry for the things. So I'm cutting edges here, and let's say that lambda of ST is the size of the maximum flow, like maximum number of edge disjoint paths. So flow, I think here like unit capacitated flow. So the maximum number of edge disjoint paths between S and T. Okay, so if this K, the bound on the cut size, equals the size of the minimum cut or maximum flow, that means that I need to find a minimum cut, a minimum cardinality cut of smallest weight. Okay, so I have got weights and cardinalities. I want not, it's now the problem is becomes simpler because I'm not looking for a cut of some bounded size, but I'm looking for a minimum size cut with some extra weight bound. And now you can think of it that actually you can think like that every edge now is like one big edge because you need to count for cardinality and some tiny weight after the decimal point. Okay, so this boils down to like adding a huge number to every weight, or like our bound suffices here, add a huge number to every weight and ask for a cut. Now forget about cardinalities and ask for a cut that has got weight at most like k times big number plus my bound. Yeah, so if this is m, then this will be like k times big number plus my target weight. And if this big number is more than my weight, or at least my weight, then this boils down to what I wanted, because I need to use k edges. I need to cut k edges because that's the size of the minimum cut. So I need to spend km on the just edges, just because I cut k edges, and I cannot cut k plus 1 edges because that's more than this budget. So I need to cut k edges, and the weights needs to total to at most w. Okay, so this problem reduces to a minimum weight cut problem without any cardinality bound. If I assume that my original bound equals the size of the minimum cut, so I really need to find a minimum cut of as small weight as possible. But this reduction breaks down if we don't have the guarantee that we are looking for a minimum cut. So if you try to look for a not minimum cut, slightly larger cut, but you want small weight, then this reduction breaks down, because suddenly if you add huge weight to every edge, suddenly higher weight but less cardinality cuts become more preferable, and this reduction breaks down. So yeah, this is a problem. But now the idea here, like the crucial idea of the approach, is that, hey, maybe we can actually augment the graph in a randomized fashion. So think strange color coding, add to strange color coding to add some random choices in the algorithm so that we improve the flow, improve the connectivity of the graph. So we increase the flow between the input and the output, but keeping the solution intact. Okay, so what do we want? We have got our graph, and here is sink and here is source, and our solution that we're looking for is some cut which is like larger than lambda, than the size of the maximum flow, minimum flow or minimum cut between S and T. And now what you want to do, you want to take a green pen and add some edges to the graph, okay, so that lambda increases, but you don't break this cut. So orange one is still a cut between S and T, but lambda increases. Okay, and then we can pump up a lambda until it gets equal to k, and until it gets equal to k, and then we can use our reduction and our simple minimum weight cut algorithm. So of course, we don't know the orange solution, so we cannot just blindly add edges. We need to smartly add random edges to the graph, randomly added edges to the graph, to prove that, okay, with good probability, orange guy will stay away. I mean, will increase the flow, and with good probability, the orange guy will stay a cut. Okay, let's formalize it. So this is the statement we have. I actually, in the paper, it's slightly more complicated to handle for some special cases for the coupled min cut, but this is like the guts of the technique here. So you can do slightly more with the technique, but let's focus now on this version. That's why I wrote here restricted. Okay, So we have got a randomized algorithm that will be running in polynomial time, actually poly k times linear in the graph size, if that matters for some reasons. Okay, so we have got another directed graph, and we have got some undirected graph, and we have got designated sink and source. Okay, and there's some number of like edge disjoint path between sink and source, and there is some cut k, and actually I think it makes sense only to have it strictly larger. So let's have it strictly larger than lambda. Okay. And what we want to have got, I mean, okay, so maybe that's okay. Maybe in this formulation that actually doesn't matter because that's like quite a cumbersome. I mean, not cumbersome, but like formal from a very formal formulation. So we have got some k, and which is at least the flow of this size. And what we do, we want to add edges to the graph. Maybe we can add multiple edges. So we are fine with adding multiple edges at some moment. We add multiple edges to the graph so that the flow exceeds k. Okay, so if k equals to lambda, we don't need to do anything. We just output empty a. Okay, and the point is that if somebody gives us this orange cut, so if there's this graph, let's draw this graph here. If there's this graph here with S and T, and somebody gives me an orange cut up there, then this cut stays a cut after adding the green edges. So I'm adding green edges, okay, to the graph, and this cut stays a cut with some good probability, like inverse f of k. Okay, so that it will end up with a randomized FPT algorithm. We'll end up with a randomized FPT algorithm if we use this thing. Okay, so let's try to use this thing for our flow. For a by objective minimum cut problem. So okay, so we have got our instance with S and T. Okay, and this is some unknown solution Z, which is we can assume that that's a minimal cut. Oh, it should be orange actually. That's actually this Z is the minimal cut, the solution we are looking for. It's a minimal cut between S and T without loss of generality. So K is its cardinality. Okay, let's guess this. I mean, let's guess the cardinal. K is like we wanted cardinality at most K, so we can assume, well, like guess what's the actual size of the what's the actual cardinality of the solution we're looking for. And now let's apply this algorithm. Okay, and we will add some edges to the graph. And with this probability, okay, our solution will still be a solution, so we won't break the solution. Our new solution, I mean, the instance will be still a yes instance, or the size of the minimum weight, the minimum weight of the solution will be still the same because the minimum weight solution will stay in this graph, while the flow increases to k. Okay, so now it will reach k. It cannot exceed k because z stays a minimum cut, stays a cut, and we can apply our reduction because now our solution is a minimum cardinality cut, and we can apply our reduction to previous things. So, and we can work later in polynomial time. So with this probability, this runs in polynomial time, and with this probability, z stays at minimum cut, and we find it using our minimum weight flow from the previous slide. Okay, so in polynomial time, with this probability, we find some. So the newly added edges are undeletable. So the newly edges are undeletable. They have got infinite weight. That's a good question. You can actually think of contracting them actually in the graph, but yeah, thanks for the question. You can actually think of contracting them, but it's easier to think of adding edges up there. Okay, excellent question. Thanks. So actually, you need to repeat like 2 to the order of k log k times this algorithm to get a constant probability, success probability, and have your standard FPT randomized algorithm. Okay, good. So that's what we are doing here. Yeah, so that's the things. Now, on the way there, I'm going to prove something slightly weaker, but it will be like only a bit weaker today. So what I'm going to do is that the first observation is that, okay, here I say, okay, I give you lambda and I give you k. I mean, you see the lambda in the graph. I give you, there's a k, and then you increase the flow to k. Okay, you want to increase, you are increasing the flow to k, and observe that it suffices if you don't care really about here being f of k. You don't care about the scale of k. To get k log k, you really need to very carefully design some probabilities of some objects. So that's quite tedious actually. But if you don't care about f of k, you actually can think of increasing this lambda by 1. Yeah, so we actually can think about having this graph with a sink and source and the unknown cut, an unknown cut that's not a minimum cut, that's not a minimum cut, but it's a minimal cut, inclusion as minimal cut, and you want to add some green edges to increase the flow. I mean, at least by 1, maybe by more, but at least by 1, and don't break the orange cut. Don't stop, don't make it to stop, so don't break it, so it's still a mini, so it's still a nasty cut in what you keep in the graph. Okay, so this is what you want to increase, and then you can repeat it at most k times until your flow reaches k, and then you're happy. That's what you can do if you don't care about this really success probability. And that's what's phrased on the next slide. Okay, and that's the thing that I'm just going now to jump to a notebook and prove to you. That's okay. I'm going to give you a randomized algorithm that starts with this picture of having S and T in the graph, and some number k greater than lambda between S and T and greater than minimum flow. And now it's going to add some green edges to the graph in a random fashion in polynomial time, okay, such that for every unknown solution here, so for every minimal cut that's of size k, and I should get strict equality here. Sorry, so k is strictly larger. So the cut I'm looking for is not a minimum cut; it's larger than minimum cut. So it's possible to add edges to the. It's possible to add some more edges to the graph. It's possible to increase the flow while keeping that cut, an ST cut. That actually the flow will increase, but the cut will stay the same. Okay. So that's the thing I want to do. And if you repeat enough times so that this one reaches k, then you get the thing from the previous slide. If you care about f of k here, not 2 to the k log k. To get 2 to the k log k, it's, as I said, the tedious calibration of some randomized choices in the process, and I don't want to go into details here of that. Okay, I just want to point out before the proof that if somebody gives you the orange, if somebody gives you the orange cut, so there's an S and T somewhere here, and somebody shows you what the solution is, this is like a proof that some object like that exists at all, yeah? Then you could actually turn this guy into a click. So add all the edges on this side of the cut and add all the edges on this side of the cut. And then there will be like two clicks. There will be 2 clicks with orange edges in between, so that your minimum, so that Z is your only minimum cut in your graph, and you have got this becomes a minimum cut. So there exists a green solution. There exists something, but to design like that to make it clicks, you need to make it an orange. And now the challenge is to make a random choice to add much less green edges, so that for any unknown orange, the probability that you won't break it, and break means really adding an edge over it. So you cannot add an edge from the vertex reachable from S to the vertex reachable from T in the graph. Okay. The degree of S will not matter actually. Yeah, so that's degree of S will not matter. No, this will not matter. Size of the reachable set from S will not matter here. Actually, if you want me to matter about degree of S, sometimes it's easier to think that S is actually of degree K. You add something like that, but that doesn't matter. That's a technical things, I think. Yeah. So no, I don't think. Yeah, there's some questions coming. So the statement says that for every minimal cut, that's for Neil's questions, that for every minimal cut, the probability that it will survive is like 1 over f of k. Okay, 1 over 2 to the poly k. So it won't survive all the minimal cuts. It's just we're looking, the analysis thinks of, we're looking at some unknown orange cut, and we want to have with good probability keep it intact. We don't want to connect a guy reachable from S with a guy reachable from T. So the statement says that for every fixed solution you're looking for every fixed minimal cut, the probability it will survive is small. So you think of adding these green edges like sparsifies the family of minimal cuts, but every single minimal cut survives with good probability. Does that answer your question, Neil? I hope so. Okay, thanks. Okay, good. Okay, so now what I'm going to do here is that now I'm reached like the statement. So now I'm going to try to draw some pictures. So I'm going to change to a notebook, and let's try to do. Let's try to draw pictures. So what do we want to do? Let's recall the picture we are working here. So we are really having this S and T on these 2 sides. Okay, they're far away from each other. That's like one of the things that, it's good to think that they're very far away from each other. That's a very helpful picture. And there's some unknown cut in the middle. There's some unknown cut in the middle that we want to like, there's some lambda, which is like, okay, so our size of Z is K, which is larger than lambda of S from S to T, so the size of flow from here. Okay. And now we want to add some edges up there, and we want to increase the flow. So we don't care at the moment about reaching K with the flow. We want just to increase the flow. And think the good way of thinking about increasing the flow is that you want to break all minimum cuts. So if you take, say, I don't know, this color, and there's some minimum cut here, I mean, of size lambda, okay, you want to add a green edge over it. So think of like increasing the flow means adding an edge for every minimum cut. There should be some added edge that breaks this minimum cut, that makes it stop to be minimum. And if you break all minimum cuts, then you increase the flow. That's the way of thinking about like what does it mean to increase the flow in your graph. Okay, so we need to understand the space of minimum cuts to work here. Okay, so that's like so it's important to understand the space of minimum cuts with this picture. So what I want to do is that I want to start with S and draw T on the very far right. Okay, and now I want to draw a sequence of minimum cuts. So as you've probably seen on important separators, minimum cuts have got the submodularity property, which means that there is like the leftmost minimum cut and the rightmost minimum cut. Yeah, the one closest to S and the one closest to T. So let's take a pink color or violet color, and let's draw the cut. I will draw it like that. This is the cut. Oh, maybe actually, sorry, let me draw edges. Maybe it will be better. So so they're actually like, say, the minimum cut is of size 5, and this is like a minimum cut. This is the leftmost minimum cut. Okay, and these are like the guys reachable from S up there. So this is the leftmost minimum cut, call it C1. Okay, so this leftmost minimum cut. And now do something that maybe you have already seen on some of the, like, this is not a trick that haven't been applied anywhere. So now I want to look at the next minimum cut. There's no good definition of next minimum cut, but I want to make the following. I want to say, okay, let's make these guys undeletable. So let's take these guys, including these edges, undeletable. So like think of contracting them onto S, and let's look at the next minimum cut. So there will be like the next minimum cut. So I make this guys undeletable, including the violet edges, because otherwise this still is a minimum cut. And I'm looking for the next minimum cut. So this is like the first disjoint minimum cut. So this is the leftmost disjoint minimum cut. Okay. So I'm looking, and there's something in between, and there's this like cut 2. Okay, and this is like, say, this is block 0 and this is block 1. Okay, this is something in between. And I repeat this process. I take block 0 and block 1, including the cut C2, make this undeletable, I contract it onto S, and look for the next disjoint cut. Okay, and I proceed with this process. So let me draw this picture a few more times. Okay, and at some moment there's no more minimum cut and we reached T. Okay, so what I have done, I'm just doing, let me draw this picture here. It's not essential to be very precise here, but I want to make an overview picture, and in the end we reach T, and this is like C3, C4, up to some, I don't know, C B capital N. Okay, and the blocks are B2, and this will like block Bn minus 1, and this block Bn. Okay, so these are called blocks, and I'm just taking a leftmost minimum cut closest to S. Okay, contract it onto S, take the next one disjoint, etc. Okay, so this is some approximation of the space of minimum cuts. Okay, so if you look at now at minimum cut, I mean, then this minimum cuts, I mean, these are not all minimum cuts in the graph, but this is sort of like a good like drawing of the space of the minimum cuts here, or it turns out to be very helpful. Okay, and now comes one of the main tricks that makes this thing observe. Let's try to, I'm just going to group this. So this is, I think this is one of the main tricks of the techniques. I'm going to group these blocks into something which will be called bundles. So I will be grouping blocks into bundles. And yeah, so the first one, there's this special block at the beginning that contains S. This is like a special bundle. I will call the bundles with letter D. So this is bundle D. D0, okay. And then what I'm going to work was, for bundles, I will use, say, blue color, okay. So bundles, I'm going to go over these blocks and look at which moment, so I'm taking this block, so I'm taking this block, next block, and I'm taking blocks taking the union of these blocks, including the edges in between, and I'm waiting for the moment when everything becomes connected. Okay, because let's make a picture. Let's use the pink color and make a picture, an insightful picture here. Okay, this was minimum cut, and this was minimum cut. This cut on this picture is of size 5, which means that maximum flow is of size 5. Okay, how does maximum flow looks in this picture? So if you're a bit skilled with maximum flows, you understand that this flow actually will look like this. It will continue monotonously through the blocks and reach T. And it will continue through the blocks and reach T. It will continue through the blocks. So there will be 5 flow paths, edge disjoint paths. Okay. And it will be like it will visit this. I mean, it needs to visit first the first minimum cut, then it needs to visit the second minimum cut, etc. So this is the maximum flow, and it visits in the in this order. Okay, but here in between, the graph may have some extra edges or vertices. There may be some connections here. Okay, there may be some connections here. Okay, like that, say, and maybe some edge here and some edge here and some edge here. Okay, and now I'm scanning these blocks, say starting, I mean, the first one is like a special block, so I put it inside, and then I scan from here and look at the first moment. So let's use the blue color now, and I'm looking for the first moment when everything becomes connected. Okay, when everything becomes connected. Okay, this is this moment. Yeah, here I have got 3 connected components. Inside block 1, there are 3 connected components. The first 2 flow paths, the third and fourth, and the 5th flow path are 3 separate connected components. Then, after I add block 2, the first connected component, the second connected component gets connected. So I'm just looking inside every block, and I'm looking at the connected components there. Okay, I'm assuming that the graph is connected because only the connected component with S and T matters for this problem, so I can discard everything else. Okay, so I'm looking inside every block, just at the induced subgraph of the block. I'm just looking at the induced subgraph of the block, and I'm observing that there are these parts of the flow paths inside. Okay, there are parts of the flow paths inside. So they're like, so I'm really so I'm really looking at like, okay, how does the flow paths, these pieces of the flow paths of this violet maximum flow, how they're distributed between connected components of G induced by B1. By the graph induced by the block 1. Okay, and in this picture, I have drawn that there are some edges and connections here, like here and here. This is an example. In this example, the elements of the first 2 flow paths are together in one connected component, and there's the elements of the 2 flow connected component. Here, this is the third flow connected component, the third connected component. Okay, and now I look at G induced by B1 union B2 and union the cut in between. So I mean, these are crazy enough, but I will add explicitly this cut in between, C2. Okay, this cut in between, and then I'm checking whether how much connected components is up there. So in this picture, there are actually 2 connected components. Okay, because now this connection connects the first connected component with the second one, but still the 5th flow path is a separate connected component here in this picture. Okay, and then if I look at G, thanks for the questions. I mean, it's like the crucial moment of the entire proof. So like, it's good that you're like keeping track. So now we are looking at 3 blocks, and this now stays connected, okay? Because there are edges like that, and now this last block, this last flow path gets connected, and now everything gets connected, okay? So I stop my bundle just before it, okay? So I say this up to this moment, just before everything gets connected. This is my first. This is my first bundle. This is my first bundle, okay? And now, okay, so, and then I stop, okay, this was my first bundle, and I repeat the process. So I draw a line here, okay, this was my first bundle, okay, up until the first moment of everything becomes connected, but I stop just before. I don't allow it to be connected. So let's make another picture. Let's say that here it's actually a lot of edges added, so maybe like that, and maybe some extra edge like that, and maybe extra like that, okay? So now for the next bundle here, okay, I start from here. If I look at just G induced by this bundle, so this is bundle 3, this is disconnected. It has got 2 connected components. The first 3 flow paths and the remaining 2 flow paths are 2 different connected components. But then if I look at the G B3 union B4, then it's connected. It's connected because there's an edge connecting the third and the fourth flow path, but also like there's so many connections in B4 on this picture that everything becomes connected. So now Okay, so as I said, I stopped just before things become connected. So just this block becomes my D2, becomes D2. It should be D1 in blue, not in violet. Sorry for that. Okay, so this is my D2. Okay, and now what should I do? Now I should start here, but already now my first block is already connected, which may happen. And then I say, okay, this is a special case. This is a bundle on its own, D3, and this is called connected bundle. Disconnected bundles. So these are like normal bundles or disconnected bundles, and this is a connected bundle because I just started with a block and this block was already connected, so I couldn't stop just before the first connected one. Okay, and maybe there's actually like some extra things up there, so maybe there's like connections like here, maybe connection here, maybe connection here, and maybe some connection here, and then the entire remaining thing becomes one big bundle because it never gets connected until very end. So this becomes, yeah, because at some moment we reach T, and before getting connected, and then this is the last bundle. So in this picture, there will be like one last bundle because the last flow path will never get connected to the rest until T. Okay, so this is my last bundle. Okay, great. I think there's actually, it's easier. I mean, it's a technical marginal situation, but I think it's easier to actually cut it away and treat the last one as a special bundle or something like that. But don't worry about the last bundle. It's actually really not that important to worry. I mean, you can trick it, you can gadget it out with some extra things. So don't worry about the endpoints. It's just a technical matter, irrelevant technical matters for the endpoints. Okay, so that's the partition to bundles. Okay, so I partitioned the bundles. Bundles are very normal. They're like maximal things before everything gets connected, or just connected because I mean, there was one block was already connected. Okay, so now the observation. Now, why did I do it? They're like this definition of a bundle, as will turn out in a moment, is a very delicate definition that has got two very important properties. The first important property is the following. So there are two important properties. The first important property, so let me change, so I'm going to draw two bundles. These are bundles. This is like bundle say di, and the next bundle di plus one. Okay, and there's something happening before and something happening later. And by definition, and there's like a minimum cut in between. Yeah, there's cut in between, and there will be some cuts inside. Yeah, one bundle can be many blocks. Yeah, I mean there's unbounded number of blocks in one bundle. Okay, it's two bundles. And what I want to say is that if I take the union of two consecutive bundles, it's connected. Okay, the union of two consecutive bundles is connected. Okay, what does it mean? That means that if you look at my solution, so let's go back about my solution. There's some unknown minimal cut z. There's some unknown minimal cut z. It doesn't make sense for the cut to cut something here, then leave two bundles untouched, and then cut something here. Okay, recall that this is a minimal cut. Okay, so if it separated something here and separates something here, that means that there's already still some guy reachable from S, and there is some guy not reachable from S. Okay, because it cuts something away. So there was a reason for cutting. This is a minimal cut. So it already separated something from S. There's S in this direction, S in this direction. Okay, but because it's cut something later, there's actually somebody reachable from S here, because otherwise there's no sense, because there's T there. There's no point in cutting something later if nothing from here is reachable from S. So actually something here needs to be reachable from S. Okay, but these two bundles are connected, which means that at this moment already everything is reachable from S. Already everything is reachable from S. Okay, already at this moment everything is reachable from S, which means that this cutting here was actually irrelevant, because you're already here reachable from everything from S. So I mean this cut isn't minimal here. Okay, this is very undirected what I just said. I want to point out here. This is very undirected what I just say, but this is this is like, if you think of this orange cut needs to be somehow like compact. If you look at the space of bundles, it needs to be compact. It cannot leave two bundles completely untouched, because I mean in between it's cutting thing, because I mean one of the sides doesn't make sense. It's no longer a minimal cut. Okay, so it never cuts, it never really cuts, so it lives there. What does it mean? So if you define, so the corollary, if you say that the bundle is affected DI is affected, so DI is a bundle, and there is some cut here and some cut here, if some edge is orange here. So either an edge is cut here or one of these endpoints is cut. So this is an affected bundle. A bundle is affected, either there's a cut edge inside or one of the like cuts on the boundary. This cuts should be actually like violet, sorry. This one of these violet edges of this minimum cut up there is actually orange. Okay, so this is an affected bundle. And what it says is that you cannot leave two unaffected bundles in the row. So if you look, so this is an unaffected bundle. So if you look at this, like all the bundles, so let's draw a big picture of like all the bundles. Okay. Okay, then really what happens is that, hey, the cut affects some of them, but they're like somewhat continuous in the space. Okay, so it may leave one gap of not affected guy by this definition of affected, but it really but it's somehow like I mean, it affects bundles and it's like compact, so it can leave one gap of one guy of unaffected. But if you think of this space as being super long, so this can be much larger than K. I mean, the number of bundles can be abundant in K. There's actually some tiny area where there are affected bundles because it can leave only one space, and an edge can affect two neighboring bundles. Like an edge can affect. I mean, if you delete a violet edge, then both neighboring bundles are affected. So we can say that actually there are at most 2K affected bundles. So they span an area of something like, I don't know, 4K affected bundles, or order of K affected bundles. Okay, so not affected, but like the span of the affected bundles is order of K. Okay. Okay. So Neil has a question. There's Saket in front, but okay, sorry, I'm ignoring it. Sorry for that. Okay, good. So what I'm just saying here is that, okay, so actually the space, I drew too little. So you should think of them as there's a long space. I mean, a lot of blue cut, a lot of bundles, like unbounded number of blue cuts. I don't want to draw that many. And there's a big space of blue cuts. And there's actually a tiny area here of size at most 4K that contains all the affected bundles. Okay, and what I want to do is that I want to do now color coding. I want to like color code this area. I don't know which area it is, and I cannot guess it really because I mean I cannot guess it really. So and so I cannot guess really. I want to do color coding. So what I want to do, I want to take two colors.
Martin,
I mean,
but
I don't
why
know, a
can't you
yellow
guess the
color
starting and the right point of this
and the red
blocks?
color. Sorry.
Why can't you guess the like the block numbers, the starting block and the ending block?
Because okay, in this picture I can, because I mean let me just think, because if I guess it, I mean then I will have got the probability of success like 1 in n, which is fine for FPT, but it won't be fine if you want repeated applications of the same lemma. Yeah, because I mean the guess I want a polynomial time algorithm that with some probability makes it correct. So now guessing this is 1 in n guess.
Yes.
And if you want to repeat this process many times, then this will be n to the f of k. So I really want the f of k, 1 in f of k success probability, not in 1 in n, enable to make this a subroutine that you can repeat f of k times.
Okay, thanks.
Yep. So I want prefer to do color coding here, what means that I want to color with red and yellow, and I want to color this. So I will just, every bundle becomes, I mean, gets red or yellow tag. Okay, it's red or yellow, and I want to color this guy's red. I want to color this guy's red, but the two neighboring guys to color it yellow. And like this is like 4K, so if every bundle independently flip a coin, if it's yellow or red, then I have got 1 in 2 to the 4K success plus 2 success probability that actually the coloring will be like that. Okay, I mean, so that's like what I want to have. So I want the stretch of affected bundles with maybe some gaps in between. I want it to be colored red, but I want the boundaries to be colored yellow. Okay, that's I can have only 2 bundles. That's fine. It's even easier. I just guess whether they're red or bundles. I mean, they can be very few bundles. It's even easier. The problem is that there are a lot of bundles because I don't really know where my cut is. So I mean, It will be like, I mean, it will be even, let's progress there, but it will be even easier if there are only a few bundles. Okay, it's in a sense, it's easier to augment because there's small space of minimum cut, so it's easier to make flow augmentation there. Okay, so I'm doing this one. So what's the picture I got? So I don't see the orange guys. So I see the picture, and my picture is like, okay, so I now scan these bundles from left to right, and there's some like sequences of red guys and some yellow guys. I don't think that works. So I think, I mean, because you really need to be correct on the, or I mean, you want to add the union of all edges, or you want to add one? Because I mean, the problem is that you cannot like break. That's the question of Akanksha. We don't want to break the orange guy. So you want in neither of the choices to put an edge on over the orange ones. So you don't want a guess somewhere else to add an edge over your cut you're looking for. So we can't, I mean, so in some sense you want to, I don't see what's I mean, you can do the random addition, but I mean, then there will be either you have got 1 in n square success probability, which is bad for repetitive application of the lemma if you want to do it, or you're adding too many edges if you want to add union. So I don't think I understand what we try to do.
So actually what I was saying is, since there is this band of order k bundles, right?
Mm-hmm.
So we guess, so say we can have at most n bundles. So we guess what is the starting index of the bundle and what is the ending bundle. So this is
Yeah,
n
but
square
that gives you 1 in n square success probability.
No, but we try all possible n square. So here there is no randomization. We'll go over all such n square pairs, and for every choice of this ij pair, we do the randomized process.
Yes, but you want then repeat the process k times, because this increases by flow only by 1.
Okay. Okay.
That's one point. And if you want to apply it to more problems, you will be applying this algorithm f of k times, and you don't want 1 in n success probability, or you don't want n branching even once. You want really f of k, not f of k times n success probability.
Okay. Thanks.
Good. Yes, I want just the yellow bundles to be two boundary guys. I want just the boundary guys to be yellow. So I could play with the, good, okay? So there will be some yellow guys, there will be some red guys, there will be some yellow guys. I mean, that's the picture I see after all, yeah? And now what I want to do, the yellow guys are supposed, so with good success probability, assume I'm correct. So one of these red segments actually contains my solution, okay? And this is containing at most like 4K bundles. This contains at most 4K bundles. Let me stop using yellow color. Contains at most 4K bundles, okay? So now I want to like sequentially, like, okay, the yellow guys, they're disjoint with my solution. If my guess is correct, the yellow guys are entirely on the S side or entirely on the T side of my cut, yeah? They're either entirely on the S side or entirely on the T side of my cut, which means that I could just cliquify this entire bundle, yeah? Every yellow guy, I just cliquify this bundle. Just make it, I don't know whether this yellow guy is on the S side or whether it's on the T side. So I cannot just add edges to S or add edges to T, because I don't know which red block is the real block where I cut, but the yellow block is completely uncut, is completely on the S side or completely on the T side. So I could just like liquefy with the green edges. Okay, so that's what I do. Every yellow block gets liquefied with the green edges, and I also add the green edges like over the neighbors. So if I look at the red block, so if let me draw it like that. If there's a block that I color yellow, a bundle that I color yellow, it has got this incident pink edges. Okay, and I not only add the green edges inside here, but I also I also bridge all the neighboring cuts, because the yellow guy is unaffected, because that's how I try to, that was my requirements for color coding. So this pink guy, this violet guys are uncut, so I can bridge them. So I not only cliquify the bundle, but also the neighboring vertices here. I also cliquify into green click. So in this manner, like all these yellow things become like infinite capacity things. Like there's no flow problem up there. So now what I want to do, I want to focus on every, so what I want to do, I want to focus at every, Yes, I can do as well. I mean that doesn't matter whether it doesn't really matter whether I make the whole band into a green click or just every blue bundle becomes a click together with its neighboring vertices. I mean, for the flow thing, it doesn't matter what I do. I mean, I could do this or this, doesn't matter here. Okay. The interesting part happens when I look at the red bundle. So if there's a sequence of more than 4K red bundles, I know that this is this is a fake. This is fake. I mean, because now I know that one of the sequences of at most 4 red bundles is the thing that contains my solution. And they may be longer sequences of red bundles, which I know that I fake. So if there's more than fake, I just treat them as yellow guys. So I treat them as yellow guys. If there's a long sequence, I know that this is like a wrong place. I mean, this is not the place when we were looking for. This is not the solution. So we just treat them as yellow guys. So we can recolor them yellow. Okay. The interesting things happens. So you can think of now there's a lot of yellow around. Okay. And there are some segments of at most 4K red bundles. At most 4K red bundles, and we don't know which one is this contains the solution. But what we want to do, we want to look at each of them independently, and inside each of them, add some green edges. So we'll be only adding local green edges. We're adding local green edges so that we'll be adding local green edges so that the flow from the beginning to the end of this segment of red guys increases. Okay, so that the flow locally increases, and this will push an extra unit of flow from left to right, because I mean the yellow stretches are liquefied, and then every red stretch gets one extra unit of flow independently of each other. And the guys that don't contain the solution, we don't really care how we add green edges. There's one guy that contains the orange thing. There's one guy that contains the orange thing, and this is the guy when we are really want to be careful. I mean, we want to analyze that adding green edges. So we behave like every guy independently. We are afraid that it contains the orange guy, but in the probability analysis, we only focus on one guy that actually contains the orange guy that we look for, and we want to not to break the cat there. Okay. And so let's process. We are really look like we are far away, but we're really very close. So let's look at this guy and let's draw it. They're at most 4K. So there are at most 4K bundles. Okay, and this will actually, and there are these 5 cuts in between. Okay, and we think, okay, maybe this is like we behave like this is the thing that contains my solution. So there's somewhere the solution here hidden. Okay, the important property, okay, not the important property, but one of the things up there is that, hey, okay, this is the thing, but if we behave like that, and the previous guy was yellow, and the next guy is yellow, then actually this thing gets liquefied. So actually you can think like these guys are reachable from S, and this guy is reachable to T. So think like if the orange cut is here, then this entire area is reachable from S, and this entire area is reachable from T. So in some sense, this entire color coding boiled down us to a picture where we can assume that there's bounded number of bundles by 4K. I mean, this is like the intuition what happens here, that actually we're working with one stretch of red guys, and we think of like, okay, the dangerous moment is if the cut lands here. That means that the left side is completely on the reachable from S, and the right side is completely reachable from T, and we need to be careful not to break the orange cut here, okay? But there's at most 4K, and there's lambda flow paths up there, which means that there is something like 4K times lambda or these edges, or like twice endpoints of this ones. So what I want to do, I want for every endpoint of violet edge, I want to guess whether it's on S side or T side. So every violet, so let me say it precisely, every violet endpoint flips a coin if it's on the S side or on the T side, and we want that if actually the orange guy is here, then we want the guess to be correct. Okay, and that's like 2 to this exponent here. So this is fine. This is 2 to the poly k. Okay, so actually what happens is that each guy says, okay, these guys are on the S side, these guys are on the T side. Okay, and then what happens here is that, okay, now all these guys, okay, maybe this is all on the S side, maybe this is all on the S side, or maybe something starts to be on the T side here. Okay, maybe here more is on the T side. and maybe this is T T T T T S, T T T T S, T T T T S, and maybe here I have got, I don't know, T T T T T. I mean, that's an example I haven't thought it through, but I'm guessing this one's. Yes,
sorry to
exactly.
interrupt.
And regarding to the unknown orange cat, exactly, yes.
Can
So
I
this is
ask
like,
one question?
yes, somebody is saying something.
Yeah, you have many of these red blocks, right? So only if you know which block it is, you can do this guessing, right?
I'm aside every block, I'm doing this coin flip, every endpoint guess. And I want the sequence of red that contains the orange to have the correct guess. I don't care about the rest.
Okay. You do coin flip only. So
yes, I want
okay.
the guy that contains the orange cat to have the correct guess.
Okay, thank you.
Sure.
Fine.
Yeah. So this picture means, on this picture, it means that actually this cat cuts these three edges and then cuts something here so that these S's are separated and this is somewhat, and this cuts something here. I mean, this is like how this orange thing looks like. Actually, I think I will change this picture a bit. Sorry for that, having thought it through, so that this is actually TTT. And actually that means that there's actually some orange thing happening here. Okay, so that something like that. And this is not cut. Yeah, so this cut something looks like that. Like drawing up this orange cut looks like that on this picture. Okay, and now I guess this picture, and what I want to say is that now whatever happens, like this is like I'm going to be a bit hand wavy because I'm running out of time, but I want to say that at this moment, whatever happens, I decompose things into smaller pieces. Okay, because okay, let me be precise. So on this example here, what I'm going to now recurse here, okay, what I'm going to recurse here is that, hey, if the guess is correct, so I'm going to add from this place, I'm going to add green edges to all the guys guessed by S. And from this part, I'm going to add edges to all the guys guessed by T, guessed to be on the T side. Okay, so in a block when there's no orange things, these guys are perfectly happy. Okay, these guys are perfectly happy, and yeah, so so these guys are perfectly happy, and I mean when there's no orange cut here, nothing bad happens. I'm just adding some orange guys, and I'm also adding some green edges. And if in the block where I have the orange cut, if I guess the endpoints correctly, then this is on the T side, this is on the S side, like adding an edge between two guys on the S side and adding an edge between two guys on the T side, that's perfectly fine. So this is the thing I'm doing here. And now what we want to say here is that this, like, let's go over the cases, what may have happened here, so that what I want to say here on the, okay, so I underestimated time, but what I wanted to say here is that either somehow my budget of cuts, like the orange cut got split, or either I'm done or the orange cut got, I mean, I'll be recursing now on the bundles. But okay, so let's do it. Sorry, I thought, yeah, so let's do it like that. Let's look at the first bundle. I'm drawing the first bundle here, okay? And this guy, okay, I'm drawing the first bundle, and this guy has got on this side, has got all things are S, because that was to the yellow part. And on this part, on this side, well, I couldn't have all the S's here. Okay, I couldn't have all the S's here. Okay, that's impossible picture. That's an impossible picture because then this guy is unaffected. Yeah, there's no point in orange cut here. So actually there needs to be some T. Okay, there actually needs to be some T here. Okay, and now I mean the one of the ways of phrasing what we do now, we want now just to I mean there are more bundles here. Okay, and now we want to recurse. So there's like this green edges coming here. There's this green edges goes to T, and this edges goes to S. And now I want to say the following. On this picture, I want to recurse independently. Like I want to think, okay, here, this is S side and this is T side. And I want to recurse on the flow augmentation. There's some unknown part of the orange cut inside here. And I want to recurse on increasing the flow. And on the right-hand side, there is, and on the right-hand side, there is, and on the right-hand side, there is, yeah. So, and on the right-hand side, there's the remainder part. And what I want to say here is that, okay, I think I like I run out of time and I don't know how to phrase it properly. I want to say that I get one of the, so let me be sketchy now. There are three gains that I can get here. The first gain is that actually like my budget gets split. So like some orange cut lands here, some orange cut lands here, and some orange cut land here. And this is a progress in my analysis of the measure. There's another yeah, so okay, so maybe yeah, so okay, so another so if this is the picture like that, then my budget gets split. I mean, maybe this is actually on the S side and this edge is cut, so I know something from my solution. So this is one budget. Another thing that may happen is that actually everything lives in the first bundle. So this is the important special case that I want to say here, that this is all on the S side, this is all on the T side. So this is actually one bundle, and the entire cut lives here inside. Okay, the entire cut lives in one bundle, and this is the second moment when we use the definition of the bundle. Okay, when we use the definition of the bundle, because this is either a normal bundle or the connected bundle. And now I want to recurse on this bundle. I want to say, hey, actually, I want to I want to look inside this bundle and make a flow. And what I want to say here is, if this is normal bundle, then there are these flow paths inside, but the things are not connected. Okay, there are these 5 flow paths inside, but the there are 5 flow paths inside. Sorry for that. There are these 5 flow paths inside, but the things are not connected, which means that okay, that means that okay, there's connections like that inside the bundle, but something is connected. So I'm actually recursing on this bundle, but I'm actually splitting into connected components. I'm like doing flow augmentation here and guessing how does the orange size, like what's the cardinality of the orange cut in one connected component, what's the cardinality in another connected component, and that's my progress, that I actually split the orange guy into 2 different areas. And this may be so this is like one progress, and the second progress is that actually this is a connected bundle, but that means that if everything here is merged into S and everything here is merged into T, then actually my lambda increased because there's no more minimum cut inside. Yeah, because this is a connected bundle, which means that it consists of a single block. It consists of a single block, so there's no minimum cut inside. Yeah, because the next cut was this first minimum cut after the previous one. So let me wrap up. I know, sorry for being too sketchy because I panicked with running one out of time, but I want to say the following, that actually what happens here is that I guess this endpoint, I mean, I actually can, I mean, I did it like, so I guess all the endpoints, just to be clear, but either something non-trivial happens between many bundles, and then by guessing these endpoints, I'm actually really splitting the orange cut between the bundles, and that's the progress. That actually, like, I can recurse on every bundle now separately, but now the orange cut gets separated. Then that's my progress in my recursion, or like my analysis of the probability. Or actually the entire cut happens inside one bundle, because that's like an important special case. But then either it's a normal bundle, and then actually inside this bundle things get disconnected into 2 non-trivial parts, and that's my progress, that something gets split into 2 non-trivial parts, or this bundle is connected, but that means that the flow here increases. Okay, so if I want to increase the flow only by 1, then I stop here. If I want to do proper analysis, I need to recurse inside this connected component. Okay, so sorry for being slightly panicked. I know that I did, I badly panicked about time, but there's nobody afterwards. But I wanted to be hand wavy here on purpose, just to say that, just to hand wave how does this recursion works. That like here, okay, there are this batch of bundles, and either this orange cut is spread across a few bundles, and then by guessing the reachability of the violet endpoints, you can actually split the orange guys into smaller pieces and recurse, or everything is hidden inside one bundle, but then the definition of the bundle kicks into play, that either it's disconnected and it's split into many connected components, or it's connected and the flow is already increased inside these things. Okay, sorry. And I think I'm going to stop now with the proof. This is, I know that was sketched at the end, but that's like the intuition how it works. I want to go back to my last slide. I want to back over to the next slide. I want to say that my main open problem is like, please do the same for directed graphs. A number of arguments don't work. We don't know how to do it, but we also don't see any reason why it won't be possible. Why exactly almost exactly the same state of statement won't be possible for directed graphs. And actually, if you have this type of statements, you can actually quite easily prove the FPT variant by not only of the bi-objective directed cut, which is like one maybe a bit toy problem, but I think quite neat and important one. But also there's this problem of notorious of the L-chain sat problem, which is a problem that came out from also some CSP dichotomy. So you have got S and T, and you have got directed graph now. Okay, and there's some budget K, but the edges of this graph are partitioned into paths. So the edges of this graph are partitioned into paths, and each EI is a path of length at most L, and L is a constant. L is some constant of length at most L. So you can think like the edges of the graph are in packs which make a path, okay? And the guy is to delete K, like to find A inside M of size at most K, such that the union of I in I EI is an ST cut. So in a sense, you want to cut S from T, you want to cut paths from S to T, but you pay 1 to delete all edges of one path. Okay, and for L at least 3, for any constant L at 3, no, each EI is just a path. It's just a path. Each EI is just a path, some path inside the graph, some edges of some path inside the graph. Think of length 3. L equal 3 is an interesting case. L equal 3 is an interesting case. And this is an open problem with FPT parameterized by K, with L being a constant, even L equal 3 is FPT. We have got some arguments at some IPEC paper at some moment to say that actually it's an argument, there are some indications that there are like some sort of important separator like existential proof, something works there, but it's very vague. And essentially an argument that the standard methods for W1 hardness doesn't work. It's really this argument that you cannot have got too much flexibility in cuts. So we expect it to be FPT, and our conjecture at the moment is that there actually exists a directed version of flow augmentation, maybe a bit weaker version, but still. And if you have that the solution to your chain set contains a minimum ST cut, if it contains a minimum ST cut, then actually it's not that hard to make an FPT algorithm. If you know an extra property that the thing contains a minimum ST cut, then so a flow augmentation would solve a good version of flow augmentation for directed graphs would solve the chain set problem, and that's our conjecture why it's FPT, but we don't know how to make a directed version of flow augmentation. And I want to conclude for this open problem, and sorry for extending by a few minutes.
That's all right. Thank you so much for the talk. And I guess we can take some time for questions if there are any more. Okay, there's one in chat.
Yeah, there's Neil asks, how would you prove that the flow augmentation won't work? I mean, what's possible? So one of the things is that if such a statement would imply an FPT algorithm for a problem that's W1 hard, that would be a good argument against it. That's my way of thinking. So like if such a flow augmentation would give some unexpected algorithmic consequences, and that's actually why we conjecture it's possible, because we don't know any. It fits to like be exactly the missing piece that would explain a few things that we don't know FPT algorithms, but wouldn't at the same time prove any things that shouldn't be possible there. So that's actually our main version. You can try to imagine probably some like graph when the space of this cut is so complicated that they cannot hit, but that seems like quite a complicated. I mean, I don't see it easily, but it's not impossible to have a complicated argument in the sense that like the space is so complicated of this minimal cuts that you cannot like you cannot group them with these green edges. That maybe, but that seems like we haven't tried this type of arguments. Can we randomize all steps? I think
the last step also, like that is the bit doubtful one, right? You can use universal set for the last step also.
Yeah, so we're guessing some things, yeah, and recursion. I think some of the things can be actual. it's a good question. So I'm not sure about getting k log k in the exponent, because we are really playing with like distributions. So it's not a even coin flip. We are really playing with some distributions to get k log k and doing some like non-trivial calculus to actually analyze it. So, but if you don't care about it, I wouldn't be surprised if it's not all the color coding thing, but yeah, we haven't looked into it in detail. I don't know. So I don't want to cheat you. My guess is that I haven't presented anything today that's not doable, but the point is that you want to apply it many times, and then the randomization, because this randomization will add a lot of logs up there because of the because of this all these families, and that starts to have. I mean, it's not immediately a problem with like many applications, but yeah, okay.
Okay. One more. Like, can we extend this to vertex cut? I guess this is for the edge cuts, right?
So I presented it for edge cuts, and all these our things were for edge cuts. I think what I exactly presented here. So in a sense, we're not interested that much in the vertex cuts. I mean, because of the like what should I say? Like, because this in this CSP world, it's really about like deleting constraints or deleting edges up there, or like deleting constraints. Yeah, so
Okay.
that corresponds to deleting edges of the graph. So that in the CSP framework, the question about vertex cut doesn't make sense. But I think at this moment, because also what does it mean to add edges? Yeah, I mean, now you want to make some vertices undeletable, add some vertices, some connections. I mean, we don't have any immediate. I mean, in a sense, something's degenerate, so we haven't feeding it through, because I mean, now adding it. I mean, I don't know what would be the operation of adding edges. Adding some extra vertices, some undeletable vertices connect to some things, or collapsing some vertices into one. So that's not that obvious.
Okay. One more question. You have explained one difficulty during the directed case. And like, what could be the notion of connectivity used for the connectivity, if like for a
I don't know. So
setting?
that's the problem. I mean, you can try definitions like, okay, you can reach from everybody on the left to everybody on the right, or something like that, and it starts to break down. Or you can reach, we can get some connectivity patterns. Maybe there's like more hierarchy of bundles, like you get richer and richer connectivity patterns between the endpoints. I don't really know. I mean, there is like, that's one of the good questions here.
Okay, thank you.
There's a Dushan question. Something like that work on flow paths of length at most L. I'm not sure I understand it exactly. What does would L be a parameter here?
Yeah, L would be a natural parameter as well.
So if you have what bounded length flow paths, things start to be easier, because you can guess which guy from the flow path is in your solution and augment everybody else or something like that. So you can, when you have got short flow paths. So all these things start to be easy when there's a short flow path, because you can just branch which guys are in orange and which guys are not in orange, and like, or which guys are on the S side, which guys are on the T side, and like, so like get rid of one of the guys from orange for free, essentially. So whenever the length of the path from S to T starts to bounded in parameter, you can get rid of this path and that is one or orange edge by some simple branching or some simple guessing. So the problem becomes hard when it's really this picture when the S and T are on very far reach and there's a lot of stuff in between, a long sausage in between. That's the difficult picture.
Okay, thanks. Because the problem is usually harder than the cut.
Okay. I don't know. So Neil asks if there are classes of graphs that are closer when S and T are close and number of values is small. The problem is that like you end up, like, the point is that this recursion can unravel a lot of bundles. So you can have this SNT close because there's one short flow path. So the number of bundles is very small, but then you do some recursion, and then this short flow path got separated into separate connected component in this regime up here, when there's actually disconnected thing in this picture. So it gets disconnected, and suddenly when you recurse inside such picture, suddenly here you may have got a lot of bundles again from. So you may have got one bundle but that's because there's one short flow path, and once you separate it using this type of recursion, suddenly inside them unravels a lot of our flow paths. So I don't think that's like really I don't have a good answer here, but that makes these things difficult. Oh, Sakat wishes Merry Christmas. I wish also you Merry Christmas and Happy New Year, and hope the next year will be even better than this one.
Okay.
We are very optimistic.
Sorry for that. But we can only have fun now. Yeah.
Yes.
Okay. So thanks for listening, and yeah.
Yeah, thank you so much for the talk, Professor. It was great to have you.